Hello. Just starting up the broadcast. Just 1 second. All right, this is just a testing phase. We'll get into these problems in just 1 second. I'll cut this out of the larger video. Testing, writing, font. See how well that shows up. Not too good. I'm gonna close some windows, see if that works. All right, checking for glare. A little bit better. Let's see if this works. Nope, not that. Eh. Read that. Okay, looks pretty good. All right, testing that. May hear some double audio in just 1 second. Why, thank you very much for the fire live stream comment, Miss Victoria, or whoever that is. Let's see how this goes. I know I'm getting a close up right now. All right. All right, let me just make sure all of this is working. All right, well, if there is any problems in the future, just let me know. Put it inside the comments. And if you have any questions, just comment them in our posting here. I'll do a little intro in just a second. It is great to have you guys. As you can see, there's only like 1 viewer. It's okay. All right, I think that's about it for setup. I'll do my little intro and then begin. All right, let's get this set up right. How's it going, everyone? Mr. Geyser here with a live stream version of our Unit 1 multiple choice practice set. You'll see on the slides here today all of those practice problems that we have just for Unit 1. I'll be going through each of the problems themselves, answering them out, and just teaching through a couple of the main topics that we want you guys to study here. If you have any questions at all, you can always post them inside the comments, or you can leave a comment on the post on Canvas for this. At this point in time, I'm going to try and go through these questions here. If you have any questions at all, you can always list that timestamp on the actual video on what you want to go over a little further. Without further ado, we have this very first problem today. For this first problem here, we're given this graph of f of x is shown above. On which of the following open intervals is the graph of f decreasing at an increasing rate? Now, anytime where we have something that is decreasing at an increasing rate here, has to be something that has an increasing rate, which means that it's any of these graphs here. This is an increasing rate graph where this right-hand or this left-hand side is going to be a decreasing at an increasing rate. So it's decreasing at an increasing rate. While the right-hand side, this version of the graph, is an increasing at an increasing rate. Since our rate of change, this second one, the rate of change is increasing, we know we're dealing with a concave up kind of section. Since it's a decreasing graph at an increasing rate, we're trying to find something that looks like this in our f of x graph. The only section of the graph that looks like it is decreasing at this increasing rate is going to be between this value here to this value here. It's not the full length of this interval here, because this section of the graph from x is 1 to x is 2, for this small section of the graph, it is concave up. So it's decreasing at that increasing rate, but it's not going to be from here to here. In that section there, it's a concave down kind of section. So this is decreasing at a decreasing rate. The only section where it's decreasing with an increasing rate is going to be C from 1 to 2. The small important aspect here is that we're not including 1 or 2 in that interval. It's between those points. At the specific value of x equals 1, at this location here, it's not decreasing at an increasing rate or increasing at an increasing rate. It has nothing of those double kind of words there. This is known as an inflection point, where it's not decreasing or increasing at any kind of rate. It's changing between this decreasing at an increasing rate and this decreasing at an increasing rate. It's that point that changes for it. So in general, our answer here is going to be C for that first problem. For problem 2 itself, we're given this table above. It gives certain values of the function of g of x on which of the following intervals is the average rate of change of g the greatest. So we want to try and find at what point between these points here has the greatest rate of change. We know our average rate of change for AP Pre-Calculus is going to be average rate of change is equal to f of b minus f of a all over b minus a. This is a little bit convoluted way to try and write this. In general, f of something is just a y value. So we mainly look at this here from Algebra 1 and Algebra 2. We're more familiar with that setup where it's y2 minus y1 all over x2 minus x1. We're still doing the exact same kind of format here, but we want to determine between this point and this point, or this point and this point, or this point and this point has the greatest rate of change. So let's try this out here. I'm going to accidentally find a wrong version and then the right version of this problem here. So let's just erase this. Let's just shrink this down, kind of keep it up in the top right-hand corner. For this problem itself, we can just choose any two random points here and then decide if those are the right interval changes. So let's do this point of 0, -3 and 3, 6, and then that second point is going to be 2, 6 to 6, 18. All we're really doing is taking this second y value of 6 and subtracting this first y value of -3. So it's 6 minus -3 all over that second x value of 3 minus that first x value of 0. In this case, we get 9/3, where the average rate of change for that interval of 0 to 3, because that's going to be our x values here, is equal to 3, 9 divided by 3. We could go between all of these points to see which one's the greatest value. I'm going to do that second one as the greatest value here. Our answer for this problem happens to be this point to this point. Let's try and see what that average rate of change is. This second y value happens to be 18. This first y value is now 6, all over the second x value, which is 6, minus the first x value, which is 3. In this case here, we do 18 minus 6 here, and we get 9. 6 minus 3 gives us 3 again, and we end up with 3 in total. For this value here, we're selecting that the difference between these 2 points here is just the rate of change of 3, while this rate of change is also 3. We can go from any of these points here, say 2, -3, 6, or 18 here, and find that rate of change too. The final thing I want to do for this problem here, just double checking my key. Yeah. For the final problem that I want to try and do here is just isolate this 0 to this 6/18 and to see what that rate of change is. If we take that y value of 18, subtract this y value of -3, and take this all over 6 minus 0, we end up getting 18 minus -3 here, which is going to be 21 over 16, or over 6. 21 over 6 isn't equal to 3. 21 over 6 here is going to give us, 21 over 6 is going to give us not 18, 3.3. 3.33, repeating. Between those 2 points there, we have a larger average rate of change here. We want to try and showcase that our answer for 2 here, is C. Let me figure this out real quick. For this here, we want to specify that the rate of change between 3 to 6 is the highest. Let me make sure I did my math right. Yeah, that's all correct. That's all correct. Right now, I'm just trying to see. Oh, that's what it is. Okay. So for those that have already seen it, I don't know if anyone commented on it. Yeah, it's a tough crowd. Yeah, 10 out of 10. Thanks, Ian. For this here, it's not 18 minus 6 here is not 9. That's where I messed up. 18 minus 6 here is 12, and then this gives us 4. That was the mistake there. That was my bad. For this example here, we were taking this second point to this third point. This is the only time where our average rate of change is actually larger than across the whole way. So this larger rate of change here, my mistake was 18 minus 6 here isn't 9. 18 minus 6 is 12. 12 divided by 3 is 4. So we know that the point between 3 and 6 has that largest rate of change. So we know the answer here is C, past that mistake. That was my bad. We're looking now for problem 3. For problem 3, the graph of the function h is shown in the figure above. Which of the following best describes the behavior of the graph of h of x from the point P to point Q? So we want to try and describe the graph here between this point P all the way up to this point Q. For these 4 descriptions, let's move that while we're writing. For these 4 descriptions here, we're given A, the graph of h is increasing and concave up. In that case there, we know this is true. This part of the graph is increasing, so we know that's also true. And we also know that this part of the graph happens to be concave up. In this hyper-specific case, point Q, going from point Q over to about, probably down to here. This is concave down, while this is concave up. So we know that point Q happens to be an inflection point. So we can say that it's changing its rate of change at point Q there, just visually looking at it. A looks to be right, so we want to try and prove B, C, and D wrong. On the AP test, if this is right, just go for it. For B itself, the graph of H is increasing and concave down. We know this is correct for that section there, but it's definitely not concave down between P and Q. For C, the graph of H is decreasing. Well, already we know that's wrong. Same thing for D here. The graph of H is decreasing and concave down. We also know that this is wrong here. The only one that has both those correct statements, increasing and concave up, is A. So A, our first guess, was 100% right. We're now going to move on to part 4 here. I'm going to check chat real quick. Cool, great to see you guys. If you guys have any questions, I'd love for you guys to try and ask them. If not, you guys go just to the Vibe out just to try and watch through the video here. For problem 4, we're given what is the average rate of change of G over the interval of 0 to 5. Problem 4 is pretty fun. Notice that the interval from 0 to 5 is already listed in this graph here. So if x is equal to 0 here and x is equal to 5, we want to find what the y values are at those specific locations. At x is 0 and x is 5. So we know that x at 0 here is equal to 2 on our graph. So we can say this is equal to 2, but notice that x at 5 is not equal to 2 again. Notice that for this problem here, there's a hole in the graph. So x at 5 does not equal 2. Rather, notice how the graph has a solid hole filled in at this location. So when x is equal to 5, the graph is telling us that that y corresponding value is actually 7. So we know that at x equals 5, y is going to equal 7. And it's these 2 points that we use to find the average rate of change. Well, the average rate of change, again, is going to be that f of b minus f of a all over b minus a. In this case, f of b for that second point is going to be 7 here. F of a for that first point is going to be 2. B in this case was that x value of 5. A in this case was that value of 0. So then 7 minus 2 gives us 5. 5 minus 0 gives us 5. And we know anything divided by itself is just going to be equal to 1. So for these answers here, our answer for problem 4 is going to equal D. If you have any questions about that average rate of change, please let me know. The main thing that we wanted to look at here was that this hole is jumping up to 7. So that was the biggest mistake that I happened to see in class, is that people or students were using this here as that ordered pair of 5, 2. But the graph doesn't exist at that point there. The graph exists from this up to here, down to here, up until about 4.9999999 repeating right before 5. But when x equals 5, the graph jumps to 7 way up here. So that was the main kind of thing for this problem. We're going to look at problem 5 now. For problem 5 itself, suppose that for a cubic function of f, at x equals -4, the rate of change is positive. So we know that the rate of change at that point is there positive. We don't know if the graph is negative or positive yet, but we know it's at that negative value of 4. At x equals 1, the rate of change is negative, and at x equals +4, the rate of change is positive. What statement is true about the graph of f? So in general, let's just try and graph this pretty crudely. So if we have this x and y plane here, at x equals -4, we know that the graph is not positive or negative, but the rate of change is positive. So we know for anything that has a rate of change that's positive or increasing, we know we're dealing with a concave up kind of graph here. So we don't know if it's going down at that point, we don't know if it's going up at that point, but the rate of change looks like one of these halves of this parabola. At x equals 1, we have that the rate of change here changes, sorry, the rate of change is negative at x equals 1. So we know that this here is going to be like a concave down graph of some kind. These graphs here, on if it's increasing or the rate of change is decreasing, or this is decreasing but the rate of change is decreasing, is going to be at this x equals 1. So we know it looks like this at some point. The graph probably in red goes like this at the point right now. Last statement here is that x equals 4. So we have x equals 4 here. We go back to it being positive, so one of these graphs here. So we have a graph that goes up like this or a graph that goes down like that. In general, my prediction for this is going to be this red graph here goes up and then changes and goes up again like this. So it creates like a little like S kind of curve. That's my prediction for this graph. It's kind of messy right now, but we'll kind of flesh it out between these statements here. For these statements here, the graph of f has 2 maximum points on the interval of -4 to 4. Between -4 and 4 here, there's no way that there's multiple maximum points. We might be able to say that the graph itself goes up and then changes randomly way up here and then goes like that. But according to the description, part A cannot be solved. We have no idea if there is a maximum or not a maximum between that interval there. So we can get rid of that information. For C, let's make sure it's right. For B right here, so we know A is wrong, my bad. Same kind of logic goes to part B. The graph of x has 2 minimum points on the interval of -4 to +4. There's no way for us to prove that there's a minimum value at that point. All we know is that the rate of change here is positive, rate of change here is negative, rate of change here is positive. We have no idea about the extremas, that there's a maximum or minimum. So we can't say anything about B either. We're going to look at C. The graph of x has 1 maximum value on the point between -4 and 1, and 1 minimum value point between the interval of 1 and 4. So we don't know if that's the most true statement, but this is leaning towards a right answer. Let's check D real quick and see the differences between them. For D, it's saying that the graph of x has 1 minimum point between -4 and 1, and 1 maximum point between the interval of 1 and 4, between this interval here. For this reasoning, we're going to reason that C is the most correct answer, because for C's case, between the interval of -4 to +1, there has to be a maximum point between this point to this point here, because, let me look at my notes real quick. Yeah, because according to the notes itself, if -4 has a rate of change that's positive, and then there's a rate of change that happens to be negative, we know that the graph itself has to go up some amount, and then since now 1 is decreasing, we know it has to be going down at that point. So between -4 and 1, since that -4 it's increasing, and then this 1 here is decreasing, there has to be some maximum value between -4 and 1, because if 1 was decreasing, this part of the graph now is going downwards, leaving a maximum over here. We have no idea if this is a global maximum, meaning that it's the largest value across the whole graph, or just a local maximum, meaning it's just a maximum in regards to the y values in the neighborhood of this graph. But we can say that it's a maximum of some kind. The reverse logic is shown between the interval of 1 to 4 here. If at 1, the graph here is decreasing, and then the graph here at 4 is increasing, we know that this graph here has to be going down at some point and then going up again at 4. So there has to be a minimum value between 1 and 4, some local minimum, and then some local maximum, could be a global maximum, we don't know, some maximum between -4 and 1 here, so C has to be the only right answer. Beautiful job. D here doesn't make sense, it's just reversed. So we know that there's at least 1 maximum between -4 and 1, and 1 minimum between 1 and 4. If you have any questions about that, please leave them in the comments down below. We're now looking at part 6. For 6 here, a salesperson for this industrial company earns a commission of $400 for the first $10,000 of sales, and then $200 for every additional $10,000 or partial of sales. So let S of X represent the commissions earned for X dollars for sales. What is S of $75,000? For this S of $75,000, the big thing we need to keep in mind that it's every $10,000 that we gain $2,000 or of partial sales. So the first 10,000 of this 7,000 here is going to gain us $100. So we're going to write a little mini table here where we have our X value as our input of $10,000 increments, and then our Y value as our commission for these sales. So for the first 10,000, we end up gaining $100 in sales there. For the next 10,000 at $20,000, we end up getting $300 in commission. $100 from the first 10,000, $200 from that next 10,000. We can continue down at 30,000, 40,000, 50,000, 60,000. Let me move this graph up a little bit. And then at 70,000. So between these values here, between 20,000 and 30,000, we'll end up getting $500. Next value we get 700. Next value we get 9. Next value we get 11. And then at 7,000 we end up with $1,300 in commission. So for this problem now, we need to identify how much money we're going to gain on that extra additional amount of $5,000. So notice between these $10,000 increments, we're gaining $200. But for that partial amount of $5,000, how much do we gain for those sales? Well, we can reason out that we'd gain $100 based on that partial amount of sales there. So we can get a total of 1,400. However, that's not the answer to this problem. I made a mistake somewhere. If you guys can spot the mistake, I'd love for you guys to point it out. Let me try and spot this mistake here. Our answer for number 6 here, let's see, where is the mistake? Then $1,000 for each additional $10,000 or partial sale. Oh, a salesperson and that earns $4,000 for the first one. That was my bad. It was not $100 for the first. That was my bad. For this here, this is $400, so that's a plus 300 in this case, like a raw plus 300. So in this case here, yeah, that's all it is. Okay. I'm gonna redo this real quick. My bad. So the mistake is that it wasn't $100 for that first 10K. The amount of money you get is $400 for that first 10K. That was my bad. So we get $400 here. That next 10,000 gives us plus 200, so we get 600. Next 10,000 is 800. Next 10,000 is 1,000. Next one is 12,000 or 1,200. Next one is 14. Next one is 16. Now for these partial sales here, we're able to reason out that we end up getting 18,000 simply because of these or partial sales. So since we're not going over that 80,000 there, the partial sales of 5,000 between this 70,000 and this 75K jump here just awards us this $200 because it's $10,000 or partial sales. The partial sales of 5,000 here gain us that $200 bonus. So really, if we gain like another $5,000, we're not really gaining any more commissions from it, but we still end up with the answer of $18,000 here for part C. The two mistakes that I happened to make in this one was that the initial value here was $400, not $100, and that this partial sale here still gives us that $200 bonus there. If you have any questions about this, please let me know. If not, we're going to move on to part 7. Yeah, absolutely. Yeah, 1000%. You definitely got it there. Yeah, I did not notice that mistake until you posted it in chat. Yeah, that first value for that 100 or that first 10K was 400. Good spot. For this example 7 here, example 7 shows which of the following function has 2 vertical asymptotes, 1 horizontal asymptote, and no holes. So for this problem here, we're trying to identify 3 main things. 1, what causes a vertical asymptote, what causes a horizontal asymptote, and what doesn't cause a hole. In this case, we'll figure out what causes a hole and then be able to see which ones doesn't do that. For a vertical asymptote only occurs when we have a 0 in the denominator of a fraction. We'll only have zeros in the denominator of a fraction where we have these little binomials here, where it's like x minus 1. We have a vertical asymptote at x equaling 1, because as this function approaches 1, this denominator gets closer and closer to 0. So if we ever have some binomial in the denominator that isn't also in the numerator here, it doesn't cancel out, meaning that we'll have a vertical asymptote. On the flip side, if we happen to have a function where this binomial is in the numerator as well as the binomial is in the denominator, usually with some other binomial of some kind, there's a hole in this case. Even though that there is this binomial in the numerator and the binomial in the denominator, they don't cancel each other out necessarily. Rather, on the graph at x equals 1 here, the graph is going to do something, creates a little hole in the graph, and then continues to do on to that something. So this creates a hole, this creates a vertical asymptote. For our horizontal asymptotes, it has to do with these 3 cases where the degree in the numerator is greater than the degree in the denominator. The degree in the numerator is the same as the degree in the denominator, or the degree in the numerator is smaller than the degree in the denominator. We'll get to these 3 cases in just 1 second. Let's first try and find which one of these has a hole so we can get rid of that problem real quick. For problem A here, we're given these 2 binomials here. So we know that at the very bottom here, we're given these 2 problems. So we know that there is going to be 2 vertical asymptotes because these binomials don't have a counter at top. We also know that there's a 0. It crosses the x-axis at x equals 2 and x equals 4 here. It's not relevant for this problem, but it's nice to know. So we know that this one here has 2 vertical asymptotes and it doesn't have any holes. So we can check to see if it's one of these 3 cases to cause a horizontal asymptote. In the case here where our numerators equal our denominators, the exponents of our numerators equals to our denominators, we're going to get a horizontal asymptote at y equals 0. When we have this y equals 0, it's on that x-axis. We can check to see what case this is. We know that the degree in this numerator here is 5, while the degree in the denominator here is 3. So it doesn't match that case 2. Rather, it matches that case 1. For that case 1 here where n is greater than d, I'm going to have you guys hold on just for a second. I want to make sure I don't get these reversed when I tell you guys here. Unless you guys know it off the top of your guys' heads, I just want to make sure that I'm teaching you guys the right way. Let me just make sure. I apologize for this delay here. Hercules topic 1.7. Yeah. Yeah, I think you're right, V. 1000%. 1,000%. If that, yeah, 1,000%. If that N is greater than D, you do create that slant asymptote. And then for if N is less than D, you do create that, the quotient of the leading terms, 1,000%. So for this one here, this is just the quotient of the leading terms here. So quotient of coefficients. I'm going to try and write out this one fact for the slant. I want to make sure I get this one right. That was an awesome job, B. 10 out of 10. Absolutely. Nice quick work there. This one here. Cool. So for this slanted asymptote, we happen to get N is greater than D. We create a slanted asymptote at the slant of that weird ratio here. This ratio of 5/3 showcases that it's not a slanted asymptote. It's some weird asymptote. The slanted asymptote really only occurs when there's like one greater, so like 4/3. That's the weird thing I want to try and look at later on. I don't know if we can fully cover this. If you guys want to go further into this slanted asymptote, we can in class. But I think it's only when N is 1 greater than D where it creates that slanted asymptote. For the time being, we're good just to keep this at our values of, no, that's not good. Well, it rained today, so now my ceiling's dripping. We'll see how that goes. For this here, if the N is greater than D, it creates that slant. If N is less than D, you take the quotient of the coefficients leading the actual terms themselves. We'll take a look at the quotient here. For the quotient itself, we just want to try and find, like if this was this. If it was like x minus 2 to the second power, x minus 6, that didn't have that degree there. The leading coefficient is this leading term in front of both of these binomials. So in the case of A that didn't have that exponent here, we'd have this third case where the horizontal asymptote was at 1/1. You just take that quotient there. So we're going to do another version of that case here for part B. Oh, so for part A, it creates that slant asymptote. We want a horizontal asymptote. So we know that part A there for example 7 is not it. We can look at part B though. Part B does happen to have 2 vertical asymptotes. It has one here at x minus 1 and x plus 4. These here don't repeat in the numerator. We also know there's no holes, so it doesn't create anything like that. Since we have the degree of the numerator equaling 3, and the degree in the denominator also equaling 3, we know that since both degrees are the same, we can say that there is a horizontal asymptote at y equals 0. It's one of those easy cases. So for example B, it takes care of all 3 of these criteria. There's 2 vertical asymptotes, there's 1 horizontal asymptote at y equals 0, and there's no holes in that problem there. So you know B for number 7 is 100% right. We are going to look at C and D very, very quickly just to show why they're wrong. C is wrong here. So we have 1 horizontal asymptote here at x equals 4. However, in this case here where it's x squared minus 1, that's not a binomial. That there is a polynomial where we have to separate it again. So we can take that x squared minus 1. We know this is going to be a product of squares. So we know that this is going to equal x minus 1, x plus 1. So we take that binomial there and place it down here. So for part C, it actually has 3 vertical asymptotes, no holes, and since it has 3 vertical asymptotes, the denominator here is equal to 3. The degree of the numerator is also equal to 3. So in this case, we do have a vertical or a horizontal asymptote for C here, but we have 3 vertical asymptotes. For part D here, we kind of have the same thing where we have this here as separating into 2 different binomials. We have that again here at x squared minus 4. Both of these separate out to x plus 1, x minus 1, x plus 2, x minus 2. So we actually have a hole in this case where this x minus 2 and this x minus 2 cancel each other out. Even though the degree is higher in this case, they still create a hole at x equals 2. And there's 3 vertical asymptotes in this case. The degree for this one here is n equals 3. The degree for the numerator here is d equals 4. So it's that first case where it creates it's this bottom case here where it's the quotient of the leading terms. So we know that there is a vertical asymptote at 1 over 1, at y equals 1 for d. In this case here, overall, our answer is B. It fits these 3 criteria. If you have any questions, please let me know. I know I've talked at ends on this problem here, so I'm good to move on. Any questions? No. Awesome. We're now going to look at 8 here for 8 itself. Suppose that the point 2, 4 is on the graph of y equals j of x. We're going to find the point on the graph of the function with the given transformation of y equals j of x plus 2 plus 2. So all we're changing in this case is that we're adding 2 to the x value and we're adding 2 to the end result y value of j of x. All we want to showcase is that for this point here of the parent function, we have the point y equals j of x is equal to x comma y. But we can create a rule of some kind where we can transform just the x and just the y for this problem. For 8 here, For 8 here, all we want to showcase is that if we're given this point of 2, 4, whatever happens to the x is inversely affecting this x here. Whatever happening to the y is affecting it directly. What I mean to say is, since we have this transformation of j of x plus 2, the rule for the parent function of y of j of x plus 2, this rule here is that all of our x's are actually going to be subtracted by 2. All the y values that were given from j of x is just going to be added. Let's put this over here for a second. So our y values are going to add plus 2 because it's this direct connection and this inverse connection here. If we're given the point 2, 4, we just plug in those values to our new rule, where we know that for this parent function of 2, 4, we would get the output value of 0, 6 for this parent function. For this transformation, the y value is affected directly, the x value is affected inversely, and we're able to say that point 0, 6, or B, is our answer for this problem. Key points, things affecting x are inverse. So as a side example, if we happen to have y equals j of 2x here instead of x plus 2, the rule in that case would be x divided by 2, whatever the inverse function is. Same thing for if it was x divided by 2 in that parent function, the new rule would just be 2x. So it's just an inverse effect for all of those there. Dope. For this here, we're now going to take a look at problem 9. For problem 9, we're given that the function of g of x is equal to 5x plus 3x squared times x minus 5 times x minus 3 to the k power, has an end behavior defined by as x increases without bound in the negative direction. This is a long way to say as x increases the negative infinity, g of x increases to infinity. However, when x increases without bound in the positive direction, when x increases to infinity, g of x increases to infinity. What value of k would satisfy the end behavior condition of this function? So we could plug in all of these values into where k is, but rather we want to try and rationalize that this value here would be one of these values. So we want to rationalize it in general. So let's just rationalize 0 real quick. If 0 was the exponent for this problem, we know that this value here, regardless of what this becomes, negative 20, 10,000, negative a billion. If it's taken to the exponent of 0, this value here would be 1. Now, if x is increasing without bound in the negative direction here, this term here for this negative x is always going to become positive. So we know that this would become positive in the negative direction here because it's being squared. But for this term here, as x increases to the negative direction, this inner term becomes a larger and larger negative. In the end, as x increases to negative infinity, this value becomes a large positive times a large negative times 1. So we know that k isn't going to be 0 because this would be closer and closer to negative infinity because it's positive infinity times negative infinity here. So we know it's not going to be a here. I'm going to skip b. B is the right answer. I'm going to go right to C and D and showcase why both of those are wrong. The reason why we know both 4 and 6 are wrong, or really any even value in this case, is that if we have this value here being squared, what would happen is as x increases in the negative direction, this value here, as we showed, will always become positive because we're squaring it in the end. Since we're squaring it in the end here, that inner term is going to be some large or positive value. This term here is going to be some negative value. And if we make this term here 2, 4, 6, 8, 10, anything that's even, as this x value becomes more and more negative, this whole interior section here also becomes larger and larger negative. If we have a large negative number squared to the power of 4, to the power of 6, we're always going to end up with a positive value. So we can't have k equaling 4, 6, or any positive exponent because we need this exponent here, whatever this is, to be a negative number. So it multiplies to the second negative number so that that multiplies to this first large positive number to get a limit of positive infinity. For all of these here, you want to try and rationalize what the end behavior would be for these equations as x increases to negative infinity or positive infinity by just deriving what these are leading to. What I mean to say is this inner parenthesis for this binomial is leading to negative infinity as x becomes negative. It leads to a positive infinity as x becomes positive because I can rationalize that as this x here becomes larger, minus 5 is going to be some large value. For the end behaviors here, attempt to try and rationalize just what that parenthesis is doing. Is it becoming a large negative number or a large positive number here? We're going to move on to problem 10 now. For problem 10, suppose that the function of h of x is equal to x squared plus k times x minus 3 squared times x plus 5 has two imaginary roots with the integer coefficients. What values of k would satisfy these conditions? We want to have imaginary roots from this equation here. We know we're not going to get any imaginary roots from this problem here for this binomial of x minus 3 squared. Eventually what we'd solve out for this x minus 3 squared is it gives us two real roots. Same thing for this root here. For x plus 5 here, this root or this 0 is just going to be x equals negative 5, which is a real number. So we know we're dealing with this inner term for h of x. What we want to try and find is if x squared plus k is to give us imaginary numbers, we want this k here to actually be a negative value. The reason why we want this to be negative is if we were to solve this problem out, we would just have x squared plus k is equal to 0. If we subtract k, and k is some negative number then, we'd get x squared is equal to to negative k. That last step to find the root for this take is to square root both sides, and we'd end up getting x is equal to plus or minus, because that's what happens with square roots, of the root of this negative k value here. So if k here is negative, we want to make sure that k itself is positive when it's brought into the problem, because eventually we have to subtract k at some point. So if we made k 2i, we'd eventually be taking the root, the square root of negative 2i here. The square root of I itself is just going to give us negative 1. So we don't want to try and go down that route. So we know that this value here does not give us imaginary numbers. We know that for this here, we already know that anything with an imaginary number by itself is not going to give us a value. So we know b itself is wrong because we have this negative 1 here. We also know d is wrong because if we plugged in 4 to where k is, k or minus 4, we get x squared equals negative 4 here. That would give us some imaginary numbers. If we plug in negative 4 where k is, eventually we'd have x squared minus 4 is equal to 0, plus 4 to both sides, and then x squared equals 4 gives us 2 real answers. So we know this negative 4 isn't going to be it. The only value that works is c for positive 4 here. Eventually, that k there is like taking the square root of its negative value. So that's why our k value at the very beginning is plus 4. At this point here, we're going to look over at the next kind of problem for example 11. For example 11 here, we're given that this problem of what is the coefficient of x in the expansion of 2x plus 3 to the third power. For this problem, we're really trying to take a look at the Pascal's triangle. For Pascal's triangle here, we know we're going to go to the third level of Pascal's triangle. Pascal's triangle was that 1 on each side, and you keep adding the 2 numbers above it to make this larger triangle here. In this case, we don't need to go down as far as I'm going here. First, second, third, fourth, fifth row. Since we're doing this third exponent here, where we're taking 2x plus 5 times itself 2 more times, we're dealing with this third row here. For this third row, all we want to showcase is that these coefficients are what we're going to be multiplying to our a and our b value. Well, what's our a and our b value? Our a and our b value for these problems is this a here and this b here. So for that number 1 right here, all we're doing is we're taking 1 times a to the third power, plus, for this 3 here, 3 times a to the second power times b to the first power. We can see a pattern slowly start to emerge. Plus 3 again, 3 times a to the first power times b to the second power. And then this last term here, 1 times b to the third power. This is how we run through Pascal's triangle very quickly. In this case here, we're just asked to find the coefficient of x for this first problem here. We know that since this term here is a, we want to find when x is going to be by itself. That's going to be in this case here, where it's going to be 3 times a to the first power times b squared. B squared here is going to be 5 squared. So it's 3 times 2x times 5 squared. 5 squared is 25, times 2 is 50, times 3 is going to be 125. So all of these values here create 125x, making our coefficient 125, which is our value a for 11, 100% right. For Pascal's triangle here, this allows you to find specific coefficients for terms in the problem without actually mathing out the whole problem itself. We use Pascal's triangle here to try and just speed up that process. You could, if you had time on the AP exam, multiply this whole thing out and see what it would be. But for right now, we're just good to take out that first coefficient. Sweet. Now, we want to take a look at 12. For 12 here, the graph of this polynomial function p is shown, 125. No, what'd I do? What'd I messed up? No, it's 150. All right, we're good. I just looked at the chat real quick. For this problem here, we're taking a look at 12. 12, the graph of this polynomial function p is shown above. Which of the following could be an expression for p? So for this here, we want to try and get rid of two questions right off the bat. We know that since this graph here is a smiley face of some kind, meaning that it's concave up, we know we're not going to have a negative in front of our amplitude. So we can get rid of this c right off the bat. We know that c is going to be incorrect because it has that negative number at the very beginning. We now want to identify this key point here and these two key points over here. Let's first just identify these 2 points here. For those 2 points, we know that those are going to be zeros in our graph. So we know we only have 2 positive roots for our problems here. So this x here is going to be like x equals 1, and this x here is going to be like x equals 3, I believe. We know that x's are positive, so we want to try and find some binomial where we have some x is minus 1 times x minus 3. Now these values of 1 and 3 are just made up as an example, but we want to have 2 negative binomials, and then we want to have a third positive binomial of some kind, because this positive binomial is on the negative side. And since this here creates a root, we know that this x here has to be something of x plus this value here. Now there's something special about this root here, but we'll take a look at it in just a second. It has to do with its exponent. We're looking at these 2 roots here, some positive value, some positive value. Let's double check A, B, and D to see which of these give us 2 and only 2 positive roots. For A here, we have 1 positive root here of x equals 2, 1 positive root here of x equals 3, so at least we have 2 positive roots. Same thing for B here, positive root here, positive root here. Same thing for D here, positive root here, positive root here. But notice that we have this square for both of these roots for A and B. What does it mean to have some binomial with a square specifically? Well, if we're given any of these problems where we have like an x minus 2 squared, or to the 4th, 6, 8, 10, anything that's even, these roots here don't cross the x-axis. Rather, these even roots here just kiss or just touch the x-axis from whatever direction it's coming from. Meaning, if it's already in the positive direction, it comes down, just barely touches the x-axis at specifically the root of that problem, and then goes right back away from the x-axis. If it was coming from the negative direction, it'd do the same thing, go up from the negative direction, just touch the x-axis, and then shoot right back down. That's for any of these positive exponents. For this one here, we know that the negative exponent, the part of the function that has like x plus some value, some root here, has to have some even exponent. So 2, 4, 6, or 8. The only one that matches that is part D here. Part D has 2 positive roots here, where x is equal to 1, x is equal to 3, and we have a negative root at x equals to negative 2 with a even exponent, which creates that little kissing on the x-axis there. That's it. Yeah, that's it for 12. I have no more comments for 12. Looking at 13 now. For 13 itself, here we go. For 13 itself, we're going to let h of x equal negative 2x squared times x plus 2 times x minus 3. What are all the intervals of, or for which f of x is greater than 0? For this problem here, we want to try and create one of those number lines where it shows the roots of this problem here and figure out if it's positive or negative at those times. What I mean to say is, imagine you have the x-axis here, no y-axis included, but we label the roots of this problem. We know one of the roots is going to be for this x here, where x is equal to -2, and one of the roots here where x is equal to 3. So we can put both of those values on this number line. Here where x is equal to -2, and here where x is equal to 3. Notice there is a hidden third root for this problem. For this term here, if that term of x minus 3 becomes 0, the whole equation becomes 0 because it's 0 times this term times this term. If this front term of -2x squared is 0, it's multiplying these other two. So we can claim that the root of x equals 0 is that third hidden root because it's just multiplying its coefficient and then squaring itself. So 0 times 0 is 0, times -2 is 0, times those other two roots is going to be 0. So we have that third root of 0. Now, we just want to plug in 4 values into this problem here, and to see if it's negative or if it's positive. So for this case here, let's just plug in -10, some large negative value, into that equation and see what we would get. For this equation here of h of x is equal to -2 times x squared of x plus 2, x minus 3. If we plugged in -10 into this x here, -10 times itself is a positive 100, times -2 would mean for -10, we know that this value here would become negative. If we plugged in -10 for this problem here, -10 plus 2 would give us -8. It's going to be some negative number. Same thing for this one, -10 minus 3 would be -13, or it's really just some negative number. A negative times a negative times a negative is going to give us a negative as the end result. So everything past -2, the graph itself is going to be a negative graph. Usually at these points here, we should notice a change in polarity. Usually we'll see that. We might see that here. Let's try and plug in -1. That's a value between both of those now. So for -1, if we plug that value in, -1 squared is going to give us +1 times -2 is going to be some negative number. So we get a negative number here. -1 plus 2 in this case gives us a +1. So we get some positive number. In this case here, it's still going to be negative. -1 minus 3 is -4, which is just some negative value here. But since we have a negative times a positive times a negative, the end result would be some positive value. So we know between this interval, we have a positive value. So we did change polarity between this -2 here, that root. So we should expect a change in polarity between this section and this section because there's a root at 0. We're not going to, but you'll see why in a second. We now want to plug in some value between here. Let's just plug in the value of 1. We plug in the value of 1 for that first term there, for 1. 1 squared is going to give us 1 times -2 gives us negative value, so we get a negative value here. 1 plus 2 is 3, which is positive, so we get a positive value here. 1 minus 3 is still negative for this case. So we end up getting another negative value. So for this, we have a negative times a positive times a negative again. The end values for anything in between 0 and 3 is also positive. Eventually, just real quick, anything past 3 here, if we plugged in 4 very quickly, 4 squared is going to have a 16 times -2 gives us a negative value. 4 here gives us +6, so we get a positive value. 4 minus 3 here gives us another positive value. So we end up getting positive times a negative is going to be negative here. So everything past 3 is negative. But let's investigate why we didn't change polarity here just for a second. Well, it's because the exponent for that root is even. Since that exponent for that root is even, the graph in this case comes from the positive direction, just barely touches the x-axis, making that 0, and then shoots back up in the positive direction. So for the interval where h of x is greater than 0, where f of x is greater than 0, it's going to be in between -2 and 0, but we don't include 0, -2, because at those points, f of x equals 0. We don't want to find when it's equal to or greater than. We just want to find when f of x is greater than 0. So it's in between this interval and in between this interval, so we can get rid of this answer here, not -2 and 3, not between the whole interval itself, but we can keep this answer where it's going to be between -2 and 0, and then 0 to 3 here. B is going to be your answer for question 13. Absolutely. Moving on to question 14 here. For question 14 itself, we want to select the values of the polynomial k are shown in the table above. Which of the following claims and which of the claims and explanation statements could be true about k of x? For A here, the graph of k could be concave up because the average rate of change over consecutive equal length input values intervals are positive. Well, before I even attempt this problem and I read these answers, I know it's looking at like the second, third, fourth changes for this problem here. Well, I can see that the x values here are increasing equally, so I can actually find the rate of change for this problem. For these rate of changes here, the ROC, the first ROC here is just taking the difference between this second point minus that first point. So for this here, we end up getting 7 minus 1, which gives us 6. For this one here, we get 10 minus 7, which is 3. 12 minus 10 here gives us 2. So for the first rate of change, it's not constant, but it's still decreasing. So we know that for this one here, we can find the second rate of change and then try and find some more information from it. For this second rate of change, or the second ROC, we can see that 6 to 3 has a difference of 3. 3 to 2 here has a difference of 1. Since the second rate of change also isn't consistent, isn't constant, we know that this value here is at least a cubic function. The way I can try and describe that is, if the first rate of change, or the first rate of change for a function or a table here is constant, meaning all the values are the same, we know the function is linear. If the first rate of change is linear, so it goes like 1, 2, 3, 4, or like 2, 4, 6, 8, it's a linear increase, then the second rate of change would be constant, making the function quadratic. If the first rate of change is quadratic, making the second rate of change linear, making the third rate of change constant, then we know that the original function was cubic. For this problem here, since we know that the second rate of change isn't constant, we know that the first rate of change isn't linear, so we know that this function here is at least cubic. Because if it wasn't cubic and it was quadratic, then this would be linear, this would be constant. So we know this problem here is at least cubic. Because you can't really take a third rate of change here, it's just 2 of them, we don't have anything to compare. So for this problem here, the graph of k could be concave up because the average rate of change over consecutive equal length interval values are positive. Well, it's not necessarily a positive value or a negative value to determine if concavity is up or not. Rather, if the rate of change for 3 is going to be constant. So we know it's not going to be A here. Let's try and rationalize B. The graph of k could be concave up because the average rate of change over consecutive length intervals here is increasing. Okay, I like that terminology there. So let's try and figure out if this is concave up or concave down real quick. For this concavity here, if we were to graph this out, we end up getting 0, 1, 3, 7, 6, 10, 9, 12. So we end up increasing, but we're increasing at a slower and slower rate. This tells us for that first order here, we're still increasing, but we're slowing down that increasing. So we know that this graph here is going to look something like this, where it's a sharp increase and it's leveling out almost. Well, for those types of graphs that are leveling out almost, we know that those types of graphs actually look something like this. So it's a concave down graph. We know that this is a concave down graph because it's increasing, but its first rate of change is decreasing over time. So we know it's not going to be B, because we know this is not going to be a concave up graph. We just discovered that was going to be a concave down graph. Now the difference for C and D, the graph of K could be concave down because the average rate of change over consecutive length interval or consecutive equal length input value intervals are decreasing. I like that here. For D though, the graph of K could be concave down because the average rate of change over consecutive equal length interval or equal length input value intervals are negative. Well, we know they're not negative. And it's not that you have a concavity that's down if these values here are negative. Rather, we only have concave down graphs when this first difference here is decreasing, not negative. So if this is negative here, but still decreasing, then it is valid for C. But it's not just because it is negative. It's just if this is decreasing that we know that we're dealing with an increasing at a decreasing rate graph, which is a concave down graph. So we know C here for number 14 is the best answer for this case here. We're now going to take a look at example 15. For example 15, we're going to let f of x equal this problem here, x plus 4 to the third power times x minus 2 to the second power times x minus 5 to the second power all over x plus 4 to the second power times x minus 5 to the third power. The graph of f of x has a 0 at which of the following x values? Now when we're trying to find a 0 for f of x here, it cannot be a vertical asymptote and it cannot be a whole. A 0 for this graph is where the numerator has a unique 0. So I'm going to rewrite this graph pretty quick. We have this f of x is equal to x plus 4 to the third power, x minus 2 to the second power, and x minus 5 to the second power, all over x plus 4 to the second, x minus 5 to the third. For this problem here, what I want you guys to see is that even though these values here are repeating and the numerator exponent is greater than the denominator exponent, there's still a whole at x equals negative 4. Because there's that binomial in the denominator and the binomial repeats in the numerator, regardless of this exponent here, it creates a whole at that location. If the n value here is larger or the same as this denominator, it creates that whole. However, if the exponent in the numerator is smaller than the exponent in the denominator, then it creates a vertical asymptote. So there's a vertical asymptote at x equals 5 for this problem because the denominator binomial has a larger exponent than the binomial in the numerator with that smaller. Now in the hyperspecific case where the numerator for this binomial, the binomial in the numerator exponent was the same as the binomial in the denominator, if they're the same, it creates a whole. If the numerator exponent is greater than the one in the denominator, it creates a hole. If the numerator in the if the exponent in the numerator is smaller than the one in the denominator, it creates a vertical asymptote. So we know this term here creates a hole. This term here creates a vertical asymptote, really just leaving us with this value here, where at x equaling 2 creates just a 0 on the graph, meaning it crosses the x-axis at 2. So our answer for this case here is only 2. That's the only 0 on this graph here. The other ones create holes or vertical asymptotes. For 15, we get B. Nice work. We now want to try and take a look here at problem 16. For problem 16, the graph of the function h of x is shown above, which of the following statement pairs about h is true. So we want to just take a look at this concave up kind of graph here that is decreasing over time. For part A, the rate of change of h is positive and increasing. When we know the rate of change here isn't positive, it's negative because it's going down. We also know that this rate of change here is increasing because if I were to draw some tangent lines for this problem here, let's take one tangent line here where, make this one red, I make this tangent line at that specific location, we get this large negative graph. I'm going to make up some numbers here, but I'm going to try and correspond those numbers with some real data here. We know that this graph here is the slope at specifically that point there. This slope for this case is like -10. I don't know what the negative value is, but I do know that it's a negative graph of some kind. Notice that later down on the graph here, let's do orange here. We go later on this graph. We take the slope at that specific point here. We know that at this specific point on the graph, the slope is now larger because this slope here is like -5 now. I don't know what the actual value is, but I know it's less than -10 because this was a really steep negative slope. This slope here now is less negative, so it increased its value. In the same way that if we took the slope at this location, like way over here on the graph here, where at this point, this slope is like equal to -1, right? Some less negative, but still negative slope here. So the slopes between each of these points, as these points go along the graph, the slopes themselves go from -10 to -5 to -1. This is increasing even though they're negative values. So we know that this graph here is decreasing at an increasing rate. This increasing rate here are these slopes on the graph going counterclockwise, because it's going from this negative to a less negative to an even less negative. Eventually, for this graph here, I'm assuming it would turn positive eventually. So it's increasing, but the graph as it stands is decreasing over time. So for this one here, we know that the h of x is positive because it's just in that top section of the graph, and increasing, that's wrong. So we know that the graph itself happens to be positive. So this term here technically is correct, but it's definitely not increasing. The graph is going down. Let's take a look here for B. The rate of change of x is positive and decreasing. Well, we know for B here, we know that the rate of change for this graph here, nice. The rate of change here is positive and, sorry, the rate of change here is not positive for these graphs here because we know that the rate of change here is decreasing. That was my bad. That was my bad. For the rate of change for both of these here is negative. So these values are negative. So we know that the rate of change is decreasing. These values are negative. So we know that this is not a positive rate of change. It has to be negative rates of change. This value is increasing. I flip those around. The rate of change is increasing in this case. For part B here, answer B, it is not a decreasing rate of change. Rather, it is a negative rate of change that is increasing. The negative rate of change, this negative here, at an increasing rate. So we can say that D here is wrong because that rate of change isn't decreasing. That's it. Concave up has a decrease and an increasing rate. So if you also get a graph that looks like this, it has an increasing and an increasing rate. That's all. We're gonna look now at problem 17. For problem 17, we're given this problem here where the rational function of r is given by r of x is equal to 2x squared minus 13x plus 30, which is the following statements about r is correct. So for r itself, I'll just try and factor this out real quick. For factoring these out here, we're given this problem of 2x squared minus 13 plus 30. Eventually, we want to try and separate out that binomial. Ideally, the fast and dirty way to do it is we can undistribute the 2 from all 3 of these terms here. We're going to go on a very small side tangent and then come back to this problem. If this middle term here was actually 14x instead of 13x, we'd be easy to just undistribute that 2 and say 2x squared minus 7x plus 15. Oh, I got that dead spot here. Plus 15, and then we can solve this out normally. However, since we can't undistribute that 2 in a nice clean way, we could undistribute it and get like 6.5, but that's even messier to deal with. We want to try and use that C trick. That C trick is where you take A and then you multiply it by C to get this top number of 60. And you still want to try and find negative 13 in this bottom section here. So what two numbers multiply to 60 but add together to get negative 13? I actually don't know that off the top of my head. I think that's going to be 6 times 10. No, so we want to get, oh man, you guys are like seeing me solve this out right now. That's going to be negative 15 times positive 4, negative 4. No, that would still give us negative something else. So both of them are negative. Negative 3 times negative 10? Yeah. Negative 3 times negative 10. So negative 3 times negative 10? Nope, that gives us negative 30. Negative, so they both had to be negative or both had to be, yeah, they both had to be negative. So negative 6, no, negative 8 times, no. Trying to solve this out now. If anyone has it already solved, 10 out of 10, but let me try and do this, factor it out. For 17, we end up getting 18 times, what's that gonna give us? No, 18 times 5? It would have to be a negative 18 times a negative 5 to get positive 30. This value here, we want to try and get 9. No, not 9. What about, oh, 18 wouldn't work. Oh man, it's like dead air. I'm sorry. Let me try and factor this out right now. Oh, what two values multiply to that? I don't think anything works for that, right? Negative 13 times 1. I'm sorry this is stumping me right now. I'm trying to figure out what that factored version is. I don't think that's a real factored. 60 times 1, 30 times 2. I think the next one is 15 times 4 here. 5 times 8. 6 times 10. 7 doesn't go into it, and then we just repeat 8 to 5 here. Oh, it says 8 and 5. Oh, I feel silly. Well, negative 8, negative 5 is going to be our answers here. Negative 8 times negative 5 gives us 60, but negative 8 minus negative 5 gives us this here. So now, with that solved out, sorry that took me so long, we now have these values of x minus 8, x minus 15 for these solved out terms here, but we do need to bring back that value of 2 into this problem. For that value of 2 here, we can put it back into here, but since we multiplied it by 2, in that case here, we divide that a term here. So we end up getting 2x minus 4 is now equal to x minus 5 here. So now we have these two equations here versus this equation up here, where we find that we get, moving this over here, moving this up to here, this all over x minus 3. So now we just want to try and determine what these values will give us. For these values here, the graph of r has a horizontal asymptote at y equals 2. Well, does it have a horizontal asymptote at y equals 2? In this case, yeah, it would have a horizontal asymptote at y equals 2 if this was like x minus 3 squared, so our n and our d value were the same. But since it isn't, we know that we're not taking these front coefficients here, so we know that a here is not right. Let's try out b here. The graph of r has a slanted asymptote at y minus 19, or y plus 19 here. Since our n degree here is greater than our bottom degree here, but it's only greater by 1, we could divide this into here and determine what that slanted asymptote is. Unfortunately, that is what we kind of have to do, because for B, C, and D, we know all of these are going to be some type of slanted asymptote. So let's try that out real quick. For this factored version, this doesn't really help us when it comes to dividing that into there. We're going to try and divide this x minus 3 into that polynomial. When we do that, we use that long division. So for the long division itself, all we take is that top numerator of 2x squared minus 13x plus 30, and we're dividing this x minus 3. And we're still using that same kind of format of this long division. What do I need to multiply to this term here, this x, so it matches this 2x squared? Well, the only thing I need to multiply is 2x. So 2x times x here gives me 2x squared. 2x times negative 3 gives me negative 6x. And now I do keep, change, flip. So this there, that was a very important step. Notice how for this value, it's just 2x times this one here. Then I change the signs of everything, because 2x squared minus 2x here then gives me 0, getting rid of that first term. For this one here, negative 13x plus 6x here gives me 7x. I drop down the rest of this here, plus 30. And now I just need to figure out what I multiply to x minus 3 to get that value. Well, what I need to multiply is plus 7. 7 times x gives me 7x. 7 times negative 3 gives me negative 21. Now I do keep, change, flip, making that negative, making that positive. Not keep, change, flip. Just changing the polarity of everything. 7x minus 7x here. These cancel out to give me 0. And then we have a remainder of plus 51. So we know that this is the equation for our slant here. So we know that I did something wrong here because we don't get a slant of that there. Man, where did I mess up? 2x minus that is 6x. Plus that gives me 7x. We should get the answer of D. Oh, for this here, I'm trying to multiply this value of -7 here. That was my apologies. We're multiplying this value of -7 here to this x here so that we get -7. -7 times -3 here gives us +21. And now our terms cancel out. My apologies. Since it is -7 here, we're multiplying that to here to get to this term here. That's what cancels this out and gives us the remainder of 51. So this here is our slant. Since this here is our slant of 2x minus 7, we know that our answer here is going to give us D. Let me just double check that answer here, 17, D, 100%. So we end up getting this equation for that division there. If our n numerator here is 1 larger than our numerator or our exponent for our denominator, which is 1 here, then we can use the slant asymptote long division to find that slant there. Moving on to number 18. For problem 18 here, we're given this graph where the graph of the rational function r of x is shown above. Which of the following could be the expression for x? Immediately, I'm going to identify two specific terms here. The first term is going to be this x is 2 and this x is 3. So at x equals -3, we have a whole, and at x equals 2, we have a vertical asymptote. So right off the bat that's at that dead spot. For that x equals -3 for the whole, we know for this function here, at the bare minimum, we need to have x minus 3 in the numerator as well as x minus 3 in the denominator, where the exponent in the numerator is greater than the exponent in the denominator. Meaning that this was either 2, or that this was 2, that this was 2, or this was 3. Something along those lines. If the denominator here was greater, say it's 4, this would create a vertical asymptote. Keeping things simple, if we want to have a vertical asymptote at x equals 2, we just make that binomial of x minus 2 in the denominator. Now again, we could have that situation where it's also in the numerator here, but we have the exponent is smaller in the numerator in that case. We're going to just get rid of that scenario. We just have this binomial in the bottom. Notice though, we actually have a 0 at this point here. So at x equals 1, we have a 0 on the graph. So it means in the numerator, we have this x minus 1, and it doesn't have any matching at the very bottom. We also know that since we have 2 of our binomials here, 2 of our binomials here, our n degree happens to be the same as our d degree down here, and we don't have a horizontal asymptote at y equals 0. Since our n degree and our d degree equal each other right now, we would want to see a horizontal asymptote at y equals 0. Since we don't see that, we know one of these terms here has to have a square with it of some kind, so that we have one of these terms here has to have a square to it in the denominator, because if we have n is less than d, we're now just taking that front coefficient in front of both our terms here, and we just take the quotient of these coefficients to find what that horizontal asymptote is. Well, since we have a horizontal asymptote of some kind at 2, we know that the quotient for this has to be 2 of 1, or it could theoretically be 4 over 2 or 10 over 5, as long as we get 2 as that final quotient here. So we need to make this denominator larger than our numerator, and we need to have our numerator here of x minus 1, x minus 3, because we have a whole at x equals negative 3 and x equals negative 1. So this here should be positive 3, positive 3. That was my bad real quick. These terms here are x plus 3, because we have a whole at x minus 3, making that change. We have a 0 at x equals 1, so we have this in the numerator. We have this as a squared vertical asymptote because we need to make these bottom parts here, the exponents, numerator and the denominator are the same. So if n equals d, it's going to be that quotient rule for our vertical asymptotes. I'm going to recover that topic so I can go over that in class. I did not realize how poor I was with those three cases. N equals d, n is larger than d, and n is smaller than d. I'll recover that here. The main difference is that since n equals d, we now take the quotient of these leading coefficients. I'll do a side example later on this week that goes over n equals d, n is greater than d, n is minus than d, what those n's and d's mean. That was my bad for this problem. So we do get C as our final answer here, where the whole is at x minus 3, the vertical asymptote is x equals 2, and that 0 is at x equals 1. We're now looking at problem 19. For problem 19, we're given this problem where we're going to let f of x equals x squared plus 8x minus 4, and g of x is equal to 2x squared plus 5x minus 6. We're going to find all the intervals where g of x is greater than or equal to f of x. So for this problem here, all we're really trying to do is find when this value here is greater than this value. So all we really want to do is say 2x squared plus 5x minus 6 is greater than or equal to our f of x of x squared plus 8x plus 4. Now we could just solve this right off the bat and make an attempt to try and find these here. However, let's just factor them pretty quickly and then look at the factored versions of these problems. The factored version for this x squared plus 8x plus 4 here, we just want to find those two values that that add to 8, that multiply to 4 here. In that case, we do not find anything that multiplies to 8 or adds to 4. 1 times 4 there. Yeah, so we actually can't do that. So let's actually just subtract these from the sides here. So immediately when I put this into here, we can't find two numbers that multiply to 4 but that add to 8. So we can't factor at least this side here. So we're just going to try and solve this out the old-fashioned way by just subtracting and adding different things from each side. So let's try and get all of our x terms on this one side and all of our constant terms on this other side here. We're going to add 6 to both sides, add 6. I'm going to subtract 8x. I'm going to subtract x squared here, subtract x squared here, subtract 8x. Eventually, for this here, what we get is these x terms cancel out. These x terms cancel out, so we get x squared. 5x minus 8x here gives me negative 3x is less than or equal to, on this right side, these cancel out, this becomes 10. We're now able to try and bring that 10 back over. So we can say x minus 3x minus 10 ends up giving us when x squared minus 3 minus 10 is less than or equal to 0. These are still the same equation. Whatever is this true, this is also true. So let's try and factor this one out. What two values multiply to negative 10 but add to negative 3? In that case there, it's pretty fast to solve. We get negative 5 and positive 2. These ones add together to get negative 3, but multiply to get negative 10. So we can factor this one out as x plus 2, x minus 5 here. Now that we solve these out, let's reverse those. X minus 2, x plus 5. That was my bad. For now this, we're able to identify when our values here are greater than 0 by just making sure that x isn't equal to negative 5 or positive 2 in these cases. We now are able to say that this graph here on this number line between x is equal to negative 2 and x is equal to, or x is equal to -5, and x is +2 here. If it's anything less than -5 here, if this is less than -5, that's negative. If this is less than -5, that's negative, so this would be positive. Anything between -5 and 2, let's just do 0. If we plug in 0 here, we get a negative. If we plug in 0 here, we get a positive. So we get a negative times a positive, which gives us a negative value here. And in this case, when x is larger than 2 here, so let's say 3, 3 minus 2 is going to be positive, 3 plus 5 is going to be positive. We know it's going to be positive here. So we know that for this inequality, this is true from -infinity up until 5, and then we re-include 2 up until +infinity. For these values here, oh, did I mess that up? I definitely did mess that up. That is a +2. And this is a -5. Let me redo all of this. I'm so sorry. Let me just go back a couple of beats here. Is cutting out. Oh no, is the audio cutting out? I just see it now. Let's see if I can change this. Oh, that's because the microphone's dead. That's because we've been going on for nearly 2 hours. I will talk louder. Thank you for letting me know. I'm going to redo this problem here, and we're going to end at the non-calculator section. So we'll try and get the problem 25. We'll see how close we get. I'm going to redo this problem real quick. For this here, we solve this out, so we get x plus 2, x minus 5 here is less than 0. So this term here was -2. That's what I thought in the very beginning. And then that term there is +5. Luckily, our number line doesn't change. If we have a negative value here that's like -10 or -3, plugged into these values, we'd still get a positive. Anything greater than 5 is also going to be positive here. So I just really quickly fix that mistake. At this point, since this inequality is true during this interval here, we also know that this inequality at the very beginning is also true for this interval here. So for problem 19, we get the answer of D because we solved out this hidden interval that we were able to make. Now we're able to, yeah, it's gonna be cutting out for a little bit. Man, on a scale of like 1 to 10, how bad is the cutout? You guys are able to respond. On a scale of like 1 to 10, how bad is it cutting out? Because if it's cutting out, I can't auto caption it either. It's gonna end up just getting holes in it. Let's try out this question here, and then we'll just stop it at 20. Yeah, we'll just stop it at 20. For this problem here, we just want to do 20. We'll go through the rest of the problems in a secondary live stream where I figure out audio again. For this here, we're given that the graphs of the function, why did you get x squared when you did subtraction of x squared from, yeah, let's go back. Let's go back to that equation. I think I just messed up that equation. For this here, okay, so let's clean this up. I'm gonna redo part of this problem, and we're gonna stick on this problem and we'll end at 20. So let me just write it a little bit cleaner. Because I ended up making a couple of mistakes during this one here. So all I'm doing is delete, there we go. So we want to try and solve out this inequality of g of x is greater than f of x. So we're trying to do g of x is less than or equal to f of x. Immediately, I can make that equation where g of x is just this 2x squared plus 5x minus 6 is greater than or equal to f of x, which is just x squared plus 8x plus 4. Now I want to try and solve out this inequality. From this inequality, if I treat this similarly to an equal sign and I want to just solve this out, I can just bring everything to one side or bring the solving term that I want to try and solve to one side. So if I subtract x squared here and I subtract x squared here, what ends up happening is that this x squared cancels out with that coefficient, leaving me with x squared here. Now I can subtract this 8x from this side, subtracting this 8x from this side, where 5x minus 8x gives me negative 3x. And now I can also subtract this 4 from this right side, this 4 from this left side, and I get negative 10 is less than or equal to 0. From this point here, I'm now able to factor this equation by just taking 2 and 5, which gives us that factored version of x plus 2, x minus 5 is still less than or equal to 0. If we solve out this inequality, we then solve out this inequality, which solves out this inequality, which solves out our main inequality. So for that original question, it was just that little thing here. Once we're at this point, we're then able to make that number line chart where we plug in some random number that's past negative 2, that's 0, in between negative 2 and 5, and then past 5 to make that polarity chart. And then we're able to describe that this here is the answer for this inequality, which is the answer for this inequality. I know I kind of recovered that there, but I wanted to have a clean take of me explaining out 19. We're going to go over 20. At the end of 20, that's it for today. I want to make sure that the audio is a little bit better for the calculator intensive problems. So we'll redo another stream on Wednesday, on Thursday, probably not Friday, but definitely Saturday and Sunday. So for this problem here, the graphs of function f of x and g of x are shown above. Which of the following is an expression for f of x in terms, an expression for g of x in terms of f of x. So we want to try and make some correlation between this g of x and this f of x, where g of x is going to be the parent of f of x. So we have this composite function here. We want to try and make some kind of claims about this. So we can see that we have this version of the graph is kind of pretty tight for f of x. For g of x here, it's really stretched out. So since we know that the x's are stretching out, we know that the inverse thing happening is that x's are being divided. So right off the bat, we're able to say for 20 that this divide of 2 is going to be right. So we know it's going to be a divide of 2. We know it's going to be a divide of 2. Since this here is multiplying 2, since this here isn't even multiplying or adding 2, we can get rid of d right off the bat. Sorry, d off the bat. D is not right. If it was multiplying by 2, then this initial graph would then shrink. It would get tighter. So since it's 2 times x, it's not going to be from f to g here because we'd expect it to go tighter. So we know c is also wrong, leaving us with a and b here. For a and b, we just want to see if we're shifting our graph to downward. The best way to look at that is to look at where the y-intercept is. For the y-intercept here, it happens to intercept right above 1, but not quite 2. Notice again that the y-intercept here is exactly the same, meaning that there isn't a horizontal translation, meaning that there isn't a d term. So we know that g of x doesn't have a d term. I keep circling that. I mean to cross it out. So we know that b here is the actual right answer because the only thing affecting our graph here is a horizontal stretch. Thank you very much for joining me for this live stream today. I know we didn't get through all of the problems. However, I want to make sure that the audio for this isn't cutting out or it's glitchy or kind of weird. So I'm going to try and find a different microphone. I have an idea for that. If there's any questions for 1 through 20 so far, please let me know. I know some of these questions there were some mistakes and it was a little bit sloppy. However, I'm just trying to solve these off the top of my head with the best ability that I can. Thank you very much for joining me. If you have anything else, you can email me, leave them in the comments, post them on announcements, send me a pigeon, I don't care. As long as you guys let me know on what I can work out for you, then I'm good. Enjoy yourselves. I'll be kind of leaving the stream on for the next couple of minutes in case you guys want to mention something or anything. But at this point, I'm going to close down. Thank you very much. I appreciate it. Thank you, Grandpa Judy. Also for you guys here, ooh, I can like turn it a little bit. What if I do, I don't know, I can be kind of extra. I can like turn it, that's fine. If you guys have any suggestions on how to make the stream a little bit better, if it's just doing problems out a little nicer, let me know. As like a little bit of like nicer function, there's like music in the background for you guys, so at least it's a little bit less noisy. Is there anything else I can do for the stream when it comes to like animations? So, cool. Great to see you, V. Great to see you, A. Whoever those are. Great to see you guys. I appreciate you guys tuning in. If you have any questions or ideas to make the stream better, let me know. If not, take care. Have a good one. I'm just finishing up posting some links here. Sweet. All right, I'll be closing the stream off now. I'm gonna be posting this video on Canvas. If the video doesn't post or something along those lines, let me know. But at this point, have a good one. Take care. Get some rest. Please get some rest. Please go to sleep. I know this is like a side tangent. Please go to sleep for everyone. Get some rest. Get 8 hours of sleep. I'll see most of you guys tomorrow if you happen to be watching this for some free response help questions. Take care. Have a good one.